All right, you guys have about 5 minutes to go through these problems, and then we will get started. Oh, also, in-person exams are available outside the Resource Center. All right, let's get started. So for this first one here, this is pretty symmetrical, so it's not really going to make a difference which one of the two double bonds we protonate. We are going to always protonate, so it gives us resonance. But I'm going to pick the top one, so let's have this double bond attack this Br here. This is going to give us a plus at this position, because that gives us resonance, and an H at this position. From here, we are at minus 78, so we don't really have resonance come into effect. So Br can just come in, do an attack, and we will get our 1-2 product. All right, our next one, we have two different double bonds here. The one on the bottom has two secondary centers. The one on the top has a secondary and tertiary center. The tertiary center is in the resonance position. So because of that, this one is more likely to attack. So let's have this double bond come in, do an attack here. We are going to get a positive charge in H. And our double bond, we are at 40 degrees Celsius, which is warmer, so we're actually going to have resonance happen. So our other resonance structure is where these move over. We are going to get a different 5-membered ring. Comparing these two rings here, this is a double bond with 2 substituents on it. This is a double bond with 3 substituents on it. This is going to be a more stable double bond. So Cl can come in, attack at this position. And we'll get a 1-4 product. Okay, this top one is a little bit tricky for a couple of reasons. So when we do our attack of our proton, it's symmetrical, so it doesn't really matter which one we attacked with. We are going to get this carbocation here. So there were some questions in the 930 class as to why we don't get this carbocation. And the reason for that is that this doesn't have any resonance. And essentially anything that has resonance is more stable than something that doesn't. So if you're thinking of your little like chart with of increasing resonance, even a primary center with resonance is more stable than a tertiary center here. So we're always going to form a carbocation that has resonance, which means that we're always going to form this carbocation drawn in black here. Taking a look at the two resonance structures, if we shift this over, this is actually less stable. So we have a double bond with 2 substituents on it. We have a double bond with 3 substituents on it. This one on the left is actually our more stable double bond in this case, because we're just looking at which one's more stable. We don't necessarily have to choose the other resonance structure. So this will lead to our 1-2 product. Okay, the last one is really the same as this one. We just broke it out of the cyclic form. This double bond has a tertiary center at this position. That's going to be allylic versus this one over here would have a secondary. So we're more likely to form this carbocation. We are in cold temperatures, so it's not going to do resonance. It's just going to lead to the product. All right, today we are going to talk about the Diels-Alder reaction. We're probably going to spend 2 days talking about this reaction, going into all the different types of variations we can do on it. So let's get started. So the simplest form of this reaction is going to be what they call a 4+2 cycle addition. And essentially what that is you're going to have a diene, which is something with 4 pi electrons or 2 double bonds. So diene, 2 double bonds, and something called a dienophile, which really is just something with 1 double bond. When you add these two into solution together, your diene attacks this dienophile. The dienophile then will come attack your diene. You're going to form a ring. It's going to kick this last double bond down. And gives you something like this. One nice thing about these reactions is that they always make a 6-membered ring. You always have a double bond here. If we kind of try to break it into parts, so this diene here is going to be these 4 carbons, our dienophile are the 2 carbons at the end. So let's start getting into some harder ones. I'm going to kind of take it slow and then just keep adding on. So the first thing we can do is add a CH3 to our diene here, dienophile here. So we're going to have the same thing happen. This is going to attack. This is going to attack. This is going to shift over. We're going to make a 6-membered ring because we always make a 6-membered ring. We had a methyl group where this on this dienophile here. So we are still going to have a methyl group. I'm going to draw it as a dash, and I'll kind of talk about why in a little bit. But for the most part, it is plus minus. So this could also be a wedge here. Just need to know that that is a chiral center. Oh, here we go. All right. So making these more complicated. So now we have 2 substituents on our dienophile here. The way that this reaction works, I'm going to attempt to draw this in 3D, is that you're going to have your diene in solution, And then your dienophile is going to come from below to do this attack here. And because it's coming from below, it wants to get these CH3s out of the way. So it's going to do whatever it can to kind of point them downward. So when this happens, they're also going to stay in the same position relative to each other. So this is going to give us this product here where these are both on dashes. And when we started with a cis double bond, we ended with syn, which makes sense. So let's do the opposite. We can also take a trans double bond. And add these together, and as you might expect, your product is also going to be trans. Or anti, I guess, is the term for these. So going to make a 6-membered ring. Now these are going to kind of keep that configuration where they're on opposite sides. And this is going to lead to your anti-product. Let's start talking about some. We start with asymmetric molecules. So everything up till now has a plane of symmetry to it. If we get rid of that plane of symmetry, it means that we can have two different products. Let's do the simple version of it first. So these are not symmetrical molecules. When we do our reaction, this can attack here, this can attack here. We can make a 6-membered ring. With a double bond, if we think of this carbon here as being this carbon here, the methyl group we drew over here should be here. It's an sp2 center, so we don't have to worry about any stereochemistry, which is nice. We have this methyl group. We tend to draw them in the down position. This would be your product from this reaction. So I said that these are not symmetrical. And because of that, there is really no reason that we drew it like this and not this, which is essentially where you pick this up and kind of flip it over like a pancake. We take our same diene here. These two can both react together. Now this methyl is on the bottom. Six-member ring with a double bond. But our methyl is here. So these are two different products. If you're thinking about like distance away from this methyl, this is 1, 2, 3 versus 1, 2, 3, 4. They are actual different products in this case. So I always tell people to just be consistent when you're doing these flips. So I flipped the diene here. If you flipped the dienophile, that would also have been fine. What you can't do is flip both of them. So if I also try to flip this one, this is essentially my double flip product. As we flip this one over to here, we've now flipped this one over. This is going to give us this, which is just the exact same thing as your top one. So something to be careful of when you're like flipping a molecule to find out this other product. Don't flip both of them. Just pick one between your diene and your dienophile. And the reason this is the same is because it's plus minus. So this would also be this where it's a wedge. And then when you pick that up and flip it over, it turns it into a dash and makes it this product. So those are the exact same answer. Okay, more complicated one of these. Still asymmetric. We've got a cis double bond here. These are both asymmetric. They can lead to two different products. So the first product is the one that we would normally think of. Gonna make a six-membered ring with a double bond, methyl here. In this case, we have an ethyl on top, methyl on the bottom. They are cis, which means they're gonna end up syn to each other. And we can get this product. Our other option is to flip it over. So ethyl on top, methyl on bottom. You could also have the methyl on top and the ethyl on bottom. This will lead to a different product. Where now this methyl is our top group and this ethyl is our bottom group. I'm going to talk about triple bonds real quick because I think they're easier to deal with before I get into the complicated versions of these. So with a triple bond, you're really doing the exact same thing. Your double bond is going to attack one of your two double bonds from the triple bond. The triple bond is just made up of two double bonds. Kicks this one over, drops this one down. We're still going to get a six-membered ring with a double bond. We only interacted with one of the two pi bonds from our double bond, so the other one is still there. And then from this point, you're just drawing in your methyls. They don't have any stereochemistry because these are sp2. So this works out pretty well. I think these are honestly a little easier. You don't have to worry about stereochemistry in this position. It really does the exact same reaction. All right. Let's talk about some more complicated ones. So we're gonna do some rings. But we are making rings, so we're gonna do some bicyclic rings. If I start with a ring for my diene, we're gonna do a 5-membered ring first. Plus just this ethene here, or ethylene. This is going to react in the same way as it was before. So I'm going to try to draw this in 3D again. Cool. When our dienophile comes in from below and attacks, it's going to end up pushing this bridgehead of our 5-membered ring upward. We are going to make a 6-membered ring. It's going to look like a boat. And I'll draw this in 2 different ways. So I'm going to draw it the 3D way first. So this is the 6-membered ring you make. You still have the bridgehead, which means you still have those 2 carbons. And this would be your final product. You could also draw it like this here. So our 5 carbons from our cyclohexadiene here are going to be the 5 carbons that are in the middle, which are also these 5 carbons. The 2 carbons are still these 2. It's a similar pattern. I'm going to draw it again, and I'm going to throw a heterocycle in there, which I think actually makes it a little easier to see. So throwing an oxygen in this bridge position, it kind of immediately tells you where that bridge is. So when I draw this as a 3D form, it's going to look like this here. So again, your 5 carbons from your furan ring here are going to be these 5, and then the other 2 are going to be these 2. It's a little tough to draw the other way, but that would also be your 2D model for this. What's next? Okay, let's start adding some substituents on there. So I'm going to do this as the 6-membered ring also. So we have a 6-membered ring. And we're following the same rules. We are going to make a 6-membered ring like we always do. The ring is going to be between the 4 carbons of your diene and then these 2 of your dienophile. We're going to have 2 left over for a bridgehead. Before we only had 1 because it was a 5-membered ring. So it's going to look like this here. These two are syn to each other on our DynaFile. And because we're drawing them in 3D, we're just going to point them downward. If I was to draw this in 2D, it gets a little messy because we have such a large bridgehead. So we tend to not draw these ones with 6-membered rings as this 2D form, but I usually draw it out for people just to kind of help them see it. So if this is a carbon and this is a carbon, this would be your bridgehead here. These all should be plus minus. Okay, so let's take it up a notch. We're going to add in some asymmetry. So we're going to end up with 2 different products. Oops. We've got a 6-membered ring, and our DynaFile is still syn. So we're going to make a 6-membered ring that's a boat with a double bond. We're going to have a 2-carbon bridgehead here. They are syn to each other, and we're going to want them both to be pointing in the down direction. So I'm going to draw the ethyl off of this top carbon, the methyl off of the bottom one. Like before, because these are both asymmetric, they can also be rotated. So I'm going to flip on my DynaFile here to now where I have the ethyl on the top and the methyl on the bottom. This can give me a very similar product, except now the ethyl is coming off of this front one and the methyl is coming off the back. Let's move back to a 5-membered ring. Oh, sorry. Should still be a methyl off of your 6-membered ring here. These are nice because they are, again, on an sp2 center. There's no stereochemistry on them. We don't have to worry about them. All right. Moving back to a 5-membered ring. I'm going to throw the hetero atom back in there. We've got an anti-product this time. So let's draw this out. We are going to make a 6-membered ring like we always do, with a double bond. We are going to have a 1 oxygen bridgehead in this case. We have our methyl coming off of this, and then we need these to be anti to each other because they were trans to each other here. So we have an ethyl and a methyl. I'm going to draw this methyl going down. For the up, it's kind of like an equatorial. So it's going to be up and out. when you're drawing that other ethyl, that's going to be in the up position. If you want to think of it as like a wedge, this would also equate to this if I was drawing it in 2D. Okay, we're asymmetric, so we can flip this guy. Which means this can lead to a different product, which would be the same general carbon skeleton. We've switched our ethyl and our methyl here. So I'm going to draw the methyl in the up position, ethyl in the down position, plus minus. So because it's plus minus, you could also have this in the down and this one in the up. It tends to look a little messy if you do it that way. Our 2D model of this would look like oh, okay. I'll go put it there. This. Triple bonds are, again, a little easier because we don't have any stereochem. So taking almost the exact same molecule as a triple bond, we're going to still do our normal attacks. This is going to lead to, switch to, oh, that's not working. If blue will work. A 6-membered ring. With an oxygen bridgehead. Double bond here. We only interacted with one of the two bonds from the triple bond, so we still have the other one there. Throw them up group here. Now we have another sp2 center. So we don't have any stereochem here. Like before, this is asymmetric. There's no reason we couldn't just draw it like this. And this can lead to its own product. Where this methyl is now on top and the ethyl is on the bottom. All right, I'm going to talk about, I think I have one more page left. Yeah, I've got one more type of these, which it follows the same rules. We're just going to break our chains or break our rings. So for this here, I'm going to draw it in 2D. Would lead us, wait, what did I have? I had methods here. To this product, based on the rules that we've been doing so far. So something we didn't really talk about is when we do this reaction, This middle is getting pushed upward, and that's why it's showing up as wedges here. There are also two H's on the ends here, and they are getting pushed downward when this happens. You think of it as like a triangle. When you're pushing this up, it's causing these to go downward. So these are wedges. Your H's are on dashes here. If I just take this exact same molecule and split it, put a CH3 here, a CH3 here. Now we don't have a 5-membered ring, but they're going to follow the same principles. So our reaction is going to give us a 5-membered ring or 6-membered ring with a double bond. The two CH3s that are in the middle are going to get pushed up. The H's that are on the outsides would be getting pushed downward. So because of that, these two CH3s are going to end up as wedges. Just like they were wedges here. We're just not going to draw them in the middle because that would be a huge mess to write a wedge in a CH3, a wedge in a CH3 here. So it's following the same concept. You could also think of your H's as being on dashes. Like so. So now when we rotate these and do something where only one of these two CH3s is in the middle, the other one is on the outside. So if you think this is going to be the same position that this was in, there's also a little H that we're not really drawing. When this does a Diels-Alder reaction, we're going to get our 5-membered or 6-membered ring. Oh, I keep saying 5. The CH3 that was in the middle is going to get pushed up. It's going to end up on a wedge. And then this other CH3 that's on the outside is going to get pushed downward. And it's going to end up as a dash here. Okay, this is where I'm going to stop for today. On, what's today, Wednesday? On Friday, we're going to do more Diels-Alder reactions. There are some resonance-based ones that make it a little bit more complicated. We're also going to spend a lot of time reviewing the ones that we did today and go over a lot of problems on these. So I will see you guys then.